Welcome again to electromagnetism, electrostatic fields. Today we are with applications to Coulomb's law continuation, and this time instead of a point charge, we have a line of charge to calculate the field for. Here we are discussing the electric field due to a line of a charge. What happens is that we have a charge distributed over some line, thin wire, and have a density of rho L coulomb per meter. And we want to calculate the electric field at some point in the space. We already know from the previous video that E equal to the Q over 4 by epsilon naught some R square in the direction of R. But now we don't have Q. We have portion of Q which is called rho L. So we have, in this case, we can assume that we don't have E. We are, for this specific element here, we are not calculating E, we are calculating dE. So this dE will equal dQ. And what is dQ? It is simply the charge density multiplied by dL, the unit element which we are taking here. Once we do this one, to get the overall field, we need to do integration both sides relative to this dL, and then we will have our overall field. So just we are integrating over the line, and in the end we can understand that E, our electric field at this specific point here, is equal to the integration of rho L dl. This is the unit charge over again 4 by epsilon naught magnitude r square in the direction of r. So let's have some example here. We need to determine the electric field due to an infinite line. So now the line is too long, and have a charge with a constant value, this rho naught, and placed along the z-axis. So this one is x, y, z, and our line is placed in the z-axis. We just need to calculate the field at this specific point which are mentioned, but here we need to have two notes. First, this line is too long, and what will happen if it was too long? We can conclude that the electric field will be only in the rho direction. Why this happen? First, assume a point at the y-axis. What happened here is that looking from this point to this point, your vector will appear, this starting point will be 0, phi dash, and z dash, for example. But, we already say it's on the y-axis, so z here will be equal to 0. And we are at a distance rho from line, and we are at angle phi. The observation point, if you imagine in 3D, whenever you look to a point in the xy plane, in this case, your phi dash, the inspection point, and your target point of calculation will have, I mean, the phi here will be equal all. This is the first thing. Second thing, the field here, say delta E1 has two components, right? If you analyze, it will have one component in the y direction or rho direction, and another component in negative k direction. But if you have another element and this element is spaced with minus z dash, then this element, if you plot it, it will be delta E2, for example. In this one, delta E1. If you analyze this one, I mean the delta E2, it will have again component in the rho direction and another component in the positive k direction. In that case, the positive k direction and negative k direction component will always cancel each other, and you will be left with the rho direction component. So this is very important for our solution to make it easier. Now, just the typical when we do the field calculation, the most important step next is the determination of the unit vector between the point of observation and the point of calculation. So in that case, this cannot be changed. We cannot. The only thing which will benefit is this one, that phi is equal to phi dash. So we will not have a phi component, but z component and rho component will be there. So in that case, just we have here rho. We have here 0 because this lies in the x-axis. Sorry, in the z-axis. So we will be left rho minus 0, which is equal just to rho. This is the rho component here. And for z component, we have here a 0 component, and we have here z dash component. So 0 minus z dash equal to 0. And of course, we are using dash because we want to differentiate between the 2 points. And this is very important when we go to the integration because we are integrating over the line. So uh, this issues here, if we remove this writing, this point of observation here is not changing during the calculation. What it changes is our movement on the z-axis, for example, in this specific example. Only z dash will it change. And of course, in another example, maybe row phi dash or row will it change. But in this specific example, only z dash changing. So we need to know that even if was z here, either row or phi or z of the calculation point is not changed. This is very important for future also. Anyway, now we got r, then we can calculate simply magnitude of r, which is rho squared, square of this one, square of this one, and then we get the square root to calculate the magnitude. Okay, now we know r and magnitude of r, so we can use the equation which we have learned to calculate the field. So simply by substitution. Once we do this one, E will equal to this from our element is lying in the z-axis, so the L will be dz dash in this case, and rho naught is the distributed charge, constant distributed charge value, and this simply our R divided by R magnitude, which bring our unit vector, and just substitute this was constant from the beginning, and we substitute by magnitude of R, and we have a square here, so it cancels with the square root. So from step one, we understand a very important issue. We understood that the z component or the k component will be cancelled. So this will simplify the, as we have said, simplify the problem to just a constant multiplied by the integration from minus infinity to infinity because our line extends infinitely along this axis, z-axis. So simply we need to solve this integration here. Once we solve the integration, we can have our field. This integration is simple. If we replace z by rho tan alpha, and of course if we need also replace dz. So if we make dz, the rho is a constant here, and tan alpha is differentiated as 6 secant squared alpha d alpha. And we need also to understand what is the new dimensions of integration. So if you substitute by z equal minus infinity, you will get that alpha is just pi over 2, and of course minus pi over 2, and again for infinity you will get pi over 2. No, now we are just solving the integration. So we substitute here with either z or dz. This will simplify to this side, just secant square 1 over tan square alpha over 3 over 2. And of course, we are in the direction of rho. Then we know that secant square is just equal 1 plus tan square alpha. Substituting with this one, you will simplify later. Finally, you will find yourself having this integration, which is just some constant multiplied by integration minus pi over 2 to pi over 2, the alpha over secant alpha. So we can say this integration is just some kind of I. And if we calculate this one, simply secant alpha is equal to 1 over cosine alpha. So simplify more is very easy and very easy integration. You left with sine alpha from minus pi over 2 to pi over 2. And this reduced to simply 2 after mathematical manipulation. So finally, we use this value and multiply the field, and we have reached our result here. Thank you.